Hello everybody to lecture number 5 in our second semester. This session is exclusively devoted to the proof of the Hille-Yoshida theorem, which gives a full characterization of the generator of a Feller contraction semigroup on a, say, locally compact Polish space. So again, we want to work under this assumption that E is locally compact. And Polish, which will help us to prevent thinking about whether certain constructions are actually available on general spaces or not. We will work under this assumption, which is basically a safe assumption for almost everything you would want to do in measure theory. Okay, so here is the statement again of the Hille-Yosida-Ray theorem. It says this: if you have a densely defined operator, or just an operator on the if you have an operator which is defined on the continuous functions of our locally compact and Polish space E, which vanish at infinity, then the following two statements are equivalent. Namely, we can say A is, together with its domain, is the generator of a Feller semigroup, or we can equivalently say that A, together with the domain, satisfy the following three properties, namely, the domain of definition of this operator is dense. Second, the operator satisfies the full range condition for any positive lambda, which means that for any positive lambda, the map that associates every element from the domain to lambda times that element minus the operator applied to that element, which is, so we consider the operator lambda minus A, where lambda is just to be understood as lambda times identity, then this is a map which maps the domain of definition of the operator surjectively onto the space of continuous functions, so it's an onto map. That's the full range condition. And the third condition is that the operator A, together with its domain, satisfies what we call the weak maximum principle. What that actually means will be recalled in the proof of the theorem. In this case, this operator is actually closed, and the corresponding semigroup is unique, which means that whenever we have another semigroup whose generator coincides with that generator here, then this other semigroup must in fact coincide with a given one. In that regard, the generator, together with its domain, characterize in a unique fashion the semigroup. Okay, that's the statement of the Hille-Yoshida-Ray. So the statement is an equivalence statement. And we have basically seen the one direction chopped up into different small results in the previous sessions. So therefore, the only interesting part that remains to be shown is, well, to be honest, the other way around. So if we do have a generator, it's rather the other way around. If we do have a generator which satisfies these conditions 1 to 3, then we want to show that this operator is in fact the generator of a contraction Feller semigroup on our topological space, or on the set of continuous functions vanishing at infinity on our topological space. We do this proof in several steps, and the first few steps will be of preparatory nature, and only in the very last step, effectively, or almost last step, you will see how that leads to an actual constructive proof of the existence of a semigroup whose generator is the one that we're looking at. Okay, so let us start from these three conditions on the generator or on this operator, and let's show that this operator in fact is the generator of a semigroup. We start with the first observation, which is step number 0, that this operator A is dissipative on this set of functions, which means the following: that if we have a function from function space, from the definition, from the domain of the definition, then for all positive lambda, lambda f minus af as a new element in our space of continuous functions in supremum norm is larger than lambda times the initial function f in supremum norm. That's the first little remark. To show that, we use the weak maximum principle. Namely, let us choose a function from the domain of the operator, and let's choose an x from the state space such that this function assumes its maximal value, and we want to assume furthermore that this is actually the supremum of the absolute value of the function f. If that's not the case, that f assumes its maximal value or the absolute maximal value in absolute norm on a location where f is positive, we might choose to consider the negative of the function instead in order to make sure that this property is satisfied, in that case for the negative of the function f. Ultimately, our function or our statement deals with the absolute values or the norms of f, and there it's no important whether the discussion is done with f or minus f. So therefore, without loss of generality, we will assume that the function f assumes its maximal value in a location, the maximal value of its absolute value in a location where it's actually positive. Okay, since in particular this is a location where the function assumes a maximal value, by the maximum principle that we want to require, we know that the application of the operator to that function f evaluated at that position is non-positive. So if we ask for the supremum norm of lambda f minus af, then this is certainly larger or equal to any evaluation of lambda f minus af at any point, in particular at point x naught, where we evaluate that number in absolute value. But f in that position is positive, lambda is positive, and a is non-positive, so minus af is non-negative, so altogether this expression inside the absolute value is non-negative, so therefore we can omit the absolute value bars and write simply this. But again, since we know that x naught is a position or point of maximal f value, the af is non-positive, so if we subtract it, basically adds at best some values. So in particular, this number is greater or equal to lambda f of x naught alone, which by choice of x naught is the same as lambda times the supremum norm of f. So therefore we see that in fact lambda f minus af is greater or equal to lambda times f in absolute or in norm. That's exactly this dissipativity. Second statement is that we have at least a left inverse or even an inverse of this operator lambda identity minus a for all lambda. In order to convince ourselves of this, we use now the full range condition, which tells us that the image of all functions in the domain under this map lambda identity minus a is the full set of continuous functions which vanish at infinity. So therefore, if we pick any possible function of that set, we find at least one function f in the domain such that under this map the function f is mapped onto the g function. What we want to show is that there can be at most one, so that's the uniqueness. So therefore we can have an exact function f which does the job, which will then of course be the inverse, will define the inverse map of this operator, lambda minus a. For that purpose, assume we have two such functions, f1 and f2 in the domain of the operator, which both solve the corresponding equation involving the operator lambda minus a. Then, of course, we pass to the difference of the two possible solutions, and by linearity, the difference of the two solutions satisfies the corresponding equation with 0 on the right-hand side, just by linearity. And so by the just proven dissipativity, also we know that the norm of this lambda f minus af, which is on the one hand 0, by assumption it's the norm of the 0 function, but on the other hand, where the dissipativity of this operator a is greater or equal to lambda times the f norm. Yeah, lambda here was an arbitrary positive number, which tells us that the f norm of that function must be 0, and hence f is the 0 function. So therefore, there's only one, and then exactly one function f, which solves this equation, and that's exactly the definition. So this unique function f which solves this equation is exactly defining the map, the inverse map. So in other words, we have, there exists a unique map, there exists a unique f such that lambda f minus af equals g, and this f will then be called r lambda of g. And we have just convinced ourselves that there exists exactly one such thing. Okay, and we call this thing, there's another name, we give it the name lambda minus a inverse of j. Okay, so that's our definition of this inverse map, and we claim now in the next step that this inverse map is a continuous map whose norm is bounded from above by 1 over lambda, where lambda is the parameter that enters the definition of this lambda map. Why is that so? Well, if in fact G is the image of f under this R lambda map, then this means that G is the solution to the corresponding equation with f as the right-hand side. So it means that lambda G minus AG is f. That's the relation. We call that, so we said that if f satisfies this relation, that lambda f minus f equals g, then we say that f is the solution to this equation, which is defined by the operator a, the parameter lambda, and the right-hand side g. So that's the relation between f and g. And here we have interchanged the roles of f and g, which does not matter too much. We say g is r lambda of f if g is the solution to this equation, which involves the operator L and lambda, and where f is the right-hand side of this inhomogeneous linear equation. Okay, so we want to convince ourselves that this operation r lambda is a bounded operator on our space of continuous functions with operator norm bounded by 1 over lambda. So therefore assume that we study the image of an element f under the map R lambda, which means that lambda g minus ag is f. Then we can evaluate the norm of the f, the argument of this R lambda option. Well, we know that f can be represented as lambda g minus ag, but using the dissipativity which we had just observed in step number 0, this norm of this object here is bounded from below by lambda times g, which again is lambda times r lambda f. So therefore we can rearrange this equality, since so the last step was justified again by the fact that we were starting from this equality that g equals r lambda f. So we can rearrange this inequality and find that r lambda of f is bounded from above by 1 over lambda times f in norm. All this is meant to be in norm, of course, which is nothing but saying that r lambda is a bounded operator on this function space, and its operator norm is bounded by 1 over lambda. The next step is to show that we can use these r lambda functions, or these resolvents, to approximate the identity. Namely, it says that any function in function space, if we apply the resolvent for parameter lambda, multiply with lambda, and let lambda tend to infinity, then this has a limit in our Banach space of continuous functions, and that limit is the function f again. So therefore, lambda r lambda is an approximation of the identity. To show this, we start with a function f which belongs to the domain of the generator, which is a subset of all functions which we want to consider, and we we look at the difference between lambda r lambda in f and f. Well, if f is in the domain of the operator, we can use our knowledge about the inverse. We can use our knowledge about the existence of the inverse of lambda minus a. which allows us to write this f as our lambda of that thing that we obtain if we apply lambda minus a to the function f. We can apply lambda minus a to the function f because f is in the domain of the operator, but this operation of lambda minus a can be reversed by hitting the same expression with an r lambda again. So therefore, we have just blown up the representation of this f function by applying this operator in its inverse, one after the other. But now, in this representation, we have an r lambda operation, which is appearing on both sides of this difference, which we can then pull out of this difference, and therefore have behind or inside the bracket we have just lambda f minus lambda minus a applied to f. But here, of course, there is a cancellation, so therefore inside the bracket everything that's left is just the af, and we are ending up with r lambda after af. Hence, if we look at the same difference but now hit that difference with the L infinity norm using our knowledge about the boundedness of this r lambda operation, and even more that this r lambda is an operator which is bounded by 1 over lambda in operator norm. The right hand of this difference in norm is bounded from above by 1 over lambda times af in infinity norm. And since we were assuming that, of course, f is in the domain of the generator, this is a finite, the norm of this element is a finite quantity, and hence if we let lambda tend to infinity, we see that here on the left hand side we have convergence of lambda r lambda f towards f in our norm, which is the statement, this approximation statement, in the special case when f belongs and is not a general function but is a function in the domain of this generator. So therefore, if we have now really a general f, then by the assumption that the operator, or that the domain of A is dense, we can find an f prime, say, or any f with a different name, but let's call it f prime, in the domain of the operator, such that f and f prime are arbitrarily close in norm, and hence by a simple application of a triangle inequality plus, if we compare f and alpha r alpha f for this function, we can insert f prime and subtract f prime, and we can insert alpha r alpha f prime, and we can subtract alpha r alpha f prime. Using triangle inequality, we get on the right hand side a bound through the following differences. There's f minus f prime as one element, or as one sum, and then there's alpha r alpha of f prime minus f, and finally there's alpha r alpha f prime minus f prime. And now we can use the fact again that alpha r alpha is an operator which is bounded by 1 in absolute value, so therefore this is a uniformly uniformly converging sequence. And in total, if we choose alpha big enough, then this whole thing will be smaller or equal than 3 epsilon if f prime is chosen appropriately. Hence we get the claimed convergence. The fourth statement is an approximation of the operator A through expressions which involve again these resolvents or r lambda. So for any alpha positive, we introduce this A alpha operator, which is defined to be alpha times r alpha minus identity. So that's what it is. It's a bounded operator because it was just a linear combination of bounded operators which also commute. And we want to convince ourselves that for any function in the domain of the operator, A alpha f converges in fact to AF, again in supremum norm. For that purpose, we do a similar thing as before. We write the identity here as a consecutive operation or consecutive application of alpha minus A and the corresponding inverse, which, as we had seen above, allows to pull out alpha R alpha towards the front, but now we have an alpha. Let us see. So we have two alphas. So we pull out the one alpha in front is still there, and the R alpha was just pulled out. So we end up with the R alpha now standing in front of this bracket, and inside the bracket we have alpha F minus alpha minus AF. Again, there is a cancellation of the alpha F part here, and we are left with alpha R alpha AF. And we have already seen that for general functions G, alpha R alpha converges to the identity for alpha to infinity. So therefore the whole thing converges to AF. That's good to know. So we have an approximation. We have an approximation of the operator A by means of an explicit approximating sequence of operators which converge to the given operator in a pointwise sense. And these approximating operators A alpha are all bounded linear operators. So therefore we can define the matrix exponential, or just the operator exponential of these operators, which is just the usual exponential sum, where we replace the conventional product that we use for the definition of the exponential function. In the real line, we just replace this product by the product of product of operators, which is not a problem if the operators are all bounded. So therefore we can apply these operators one after the other. Here in our particular case, the operator that we exponentiate is this operator here. It is a bounded operator, and it is the sum of two operators which commute, namely the identity and the R alpha, modulo or times certain factors. But we can convince ourselves that this exponentiation formula it decomposes into the product of two exponentials if the two operators commute, which is a little bit of an exercise, or a very small exercise, but you convince yourself. So therefore, if we exponentiate, or if we take these exponential of the sum of these two operators, which is the case here, and write that as a product of two exponentials, we get as a prefactor e to the minus ta, which is the exponentiation of this identity part, together with the t and the alpha. And on the right hand side we get the corresponding exponential series for the exponential of the R alpha part. We want to argue now that each of these tt alpha maps for fixed t and alpha is a contraction, so is a linear operator on our function space of norm no bigger than 1. And in fact, if we evaluate the operator norm by subadditivity of the norm, we can just plug we give an upper bound of this norm of this exponential through the corresponding exponential series of these norms, of this norm. Since alpha R alpha is an operator of norm no bigger than 1, as we had seen, this whole exponential series, together with this prefactor of e to the minus t alpha, produces a value no bigger than 1, which shows that for each alpha and each t, the operator tt alpha is a bounded linear operator with operator norm no bigger than 1, which is what we were calling a contraction. So for each alpha, we obtain, in fact, here a contraction semigroup with regards to the t parameter. And we will now try to show that if we send alpha to infinity, then this contraction, we obtain a limit, which is, in fact, our semigroup for parameter t. To do this, we compare these tt alpha and tt beta for alpha typically other than beta. So that's tt alpha, and this is tt beta. We have two, for any values of alpha and beta, we have these different semigroups of bounded operators, which we can apply to a fixed element f from function space. And we want to estimate this difference, and we use a trick. We use a trick that we write this difference as by means of an integral of a difference of a differential of a smooth function, which assumes values in operator space. So let's consider this function as a function in the parameter S on operator space. It's a product of two matrix exponentials or operator exponentials of bounded operators. And if we evaluate this product at S equals t, we see that we have e to the a alpha times t, which is the first of these two summands applied to f. If we evaluate this product for the case when s equals 0, then this is e of the identity, which is the identity times e to the, or the exponential of t of a beta, which is exactly this term. And also we can convince ourselves that this is a smooth function assuming values in the set of bounded linear operators, which we can differentiate and then again integrate in order to obtain exactly this difference of these two values, or these two operators applied to the function f. So therefore, in total, using the fundamental theorem of calculus, we can write this difference in this Duhamel formula kind of way. That's a nice trick, and we can now do the differentiation. This looks like a differentiation in the style of a Leibniz rule, because we have a product of two functions which depend on this parameter, but now functions in operator space, but the Leibniz rule still applies. And moreover, we can of course easily convince ourselves that the operators a alpha and a beta commute, which allows us to write any order of these exponentials or alpha or beta operators in any way we like. In particular, we don't have to pay attention to the way that we write out these differentials. So let us do by Leibniz rule this differentiation with respect to the parameter. Then we get the differentiation of the first factor with respect to s first, which gives e to the s alpha, a alpha times a alpha, times the second factor, which is not differentiated. Then we get, again, by Leibniz rule, the first factor undifferentiated, multiplied with the derivative of the second factor. The second factor derived with respect to the parameter s gives a minus sign for the inner derivative of e to the t minus s a beta times a beta. Here again we see that these factors e to the s a alpha and e to the t minus s a beta appear both in the two terms of this difference, so therefore we can pull them out and write down the corresponding remaining difference, which is just a alpha applied to f minus a beta applied to f. And that whole thing needs to be integrated with respect to the time parameter ranging from 0 to t. Now, we can hit this equality with the norm. So if we just apply the norm on this equality, then on the left-hand side, of course, we get this difference that we are starting with, now evaluated in norm. On the right-hand side, we get the absolute value, or the norm correction, the Banach norm of this integral, but the Banach norm of this integral is less or equal than the integral of the corresponding norms. And here, this inside, if we we take the norm of in the space of continuous functions inside this, or of this function inside, which is a function of s. And how is the function of s with assuming values in the space of continuous functions? How is it composed? Well, it is the evaluation, or it's the application of a bounded operator of operator norm no bigger than 1 to a certain difference. So the only time dependence here inside the integral comes with this prefactor, which for all values of s is a prefactor or an operator of norm no bigger than 1. So if we use that fact, we can estimate this prefactor with a norm, or the effect of this prefactor in norm, as something which is bounded by 1. And hence, since the domain of integration is the interval from 0 to t, we get the total length of that interval times the norm estimate of this part, which is not changed over time with respect in time, which is this difference of these two evaluations of the A alpha and A beta operators on the function f. Now we wanted to consider the case, or what happens when alpha and beta are both sent to infinity. Well, if alpha and beta are sent to infinity, the difference of the left-hand side, a norm, is bounded from above by a certain factor t times the difference of A alpha and A beta applied to f. But we have already seen that for f in the domain of the operator, A alpha f and A beta f both converge to AF. So this converges to AF and this converges to AF in in Banach norms. So in particular, this limit, or the difference here, converges to 0. And hence we see that we have a Cauchy sequence or convergence sequence of these TT alpha operators when we send alpha to infinity, at least when we fix the argument. And this means that this operator TTF as the limit of the applications of TT alpha f when alpha tends to infinity is well defined, at least when f is in the domain of the generator. Now, if f is not in the domain of the generator, we can use the fact that TTF is a contraction, at least on those functions which are in the domain of the generator. And then it is a standard argument to say that if you have a function which is defined on a dense subset, a linear function in particular, which is defined on a dense subset of a Banach space, and which is bounded, then there has a unique extension to the completion to the full Banach space by just making choices of functions, the correction choices of elements of this Banach space, which converge to an arbitrary argument using the fact that this on the left-hand side will produce a Cauchy sequence. Okay, by the way, here is a mistake in my notes. I should write here, of course, that this is less or equal than f in norm. So in particular, it means that if you have a sequence of functions which is Cauchy in the norm, then the corresponding sequence of images is Cauchy. This allows you to define this extension of this operator to the full space. Okay, so in particular, we have then defined a semigroup, or we have defined a collection of operators TTF as limit of TT alpha, and it is a simple exercise to show that this is a semigroup of operators and that it satisfies the conditions that we imposed for a Feller semigroup. Particularly, it's a contraction. Okay, fine. So we have already achieved quite a bit. We have seen that if we have an operator which satisfies these conditions 1, 2, 3, say, then we can use this operator through this kind of complicated procedure to construct one semigroup of operators. And what remains to be shown is that the actual generator of this constructively obtained semigroup is the object that we started with. Right. That shall be done in the next step. Okay. We have constructed a certain semigroup using certain approximations of the operator A by bounded operators. And what we want to show now is that this semigroup, which we have obtained, generates an operator which actually coincides with a given operator. Okay, so by our abstract semigroup theory, we already know that this, since it is a good semigroup generates a certain operator, a generator which we shall denote by L and whose domain shall be denoted by D of L. We want to show now that these two operators are the same. So let us pick a function f which belongs to the domain of the initial operator. Then we can just use the differentiation of the approximating exponential semigroup for this family of bounded approximation of the operator alpha, and the fundamental theorem of calculus to write this difference between E T A alpha f and f as this corresponding integral. Again, this is an immediate consequence of this explicit formula for the exponential semigroup which we obtained for this family of bounded operators. And now we can pass to the limit when alpha tends to infinity. By definition of the limiting semigroup, the left-hand side converges to this TT, this abstract semigroup applied to the function f minus the function f alone. And on the right-hand side, we obtain, on the one hand, the first part here in this product formula converges again by definition of our semigroup T to Ts for each s, and so after a little bit of argument also for the integral, and the A alpha f converges to AF. So therefore we see that this semigroup formula for the TT semigroup, or the semigroup differentiation formula for the TT semigroup, involves the operator A, as long as the function f with which we work at this point is from the domain of the operator A. But we can now recall our definition of the generator of the semigroup L and plug this into this formula, which right away tells us that the function f will automatically lie in the domain of the generator of the T semigroup, because we can take the difference quotient here, and this is already almost the difference quotient. So if we divide this thing by T and write a 1 over T in front and pass to the limit, then immediately we get that this limit exists, and the value of the operator L applied to such function f is exactly AF. That's an immediate consequence of this formula. So in particular, we understand that the domain of A must be a subset of the domain of L, and moreover that L restricted to the domain of A must be A. And moreover, we know that from our abstract semigroup theory that both lambda minus A and lambda minus L both map onto, in a surjective fashion, their corresponding domains into the full space. So, and let me say it again, we know, of course, that lambda minus L, when restricted to the domain of A, since L and A are there the same, that this coincides with lambda minus A. So what we have here, geometrically, if you like, is that we have two domains, D of L and D of A, where D of A possibly could be a strict subset of D of L. And we have a map, namely this map lambda minus L, whose restriction onto this subset corresponds to a map that we know. And both maps are subjective mappings onto this set of functions. And then I argue that it cannot happen that, in fact, D of L is really strictly larger than D of A, because if that was the case, then we would find two different functions, one in D of A and one in D of L. But since both maps are the same, they map onto the same point. But this cannot be, because we already know that d of a is injective, which would mean that d of L, or d of L is also injective, which would also mean that the injectivity of d of L is violated. So that cannot be the case. Hence, d of L must be the same as d of A, and the two domains coincide, and therefore also the operators themselves. This shows that, in fact, the two generators coincide, namely that the semigroup which we have obtained in this constructive fashion, that its generator is exactly the generator or the operator that we started with. In particular, our operator is a generator of a semigroup. Now, we also have to prove, so the main part of our proof is completed. What remains to show is uniqueness. In this case of the semigroup, I leave this as an exercise. It's basically already done here in this previous argument under 6. You can already convince yourself basically that this is also a uniqueness statement for the corresponding semigroup. And the very last step that needs to be shown is that the operator is positive, or that the semigroup is positive. Since TT can be approximated by this sequence or by this family of alpha semigroup approximations, in order to show that this is a positive operator, it suffices to show that TT alpha is a positive operator for all alpha. If you look at the definition of the TT alphas, which involve these iterated applications of the R alpha, so the exponentiation of the R alpha resolvents, then we see that it is sufficient to convince ourselves that for each alpha R alpha, so the resolvents are positive, which is, since alpha is a positive prefactor, is the same as asking or proving that for each alpha this corresponding resolvent operator is positive. And this will be now a consequence of the maximum principle as follows. Namely, suppose we have, assume we have, correction, I made a mistake here in my writing, which can be easily corrected. So assume that we start out with a positive function f, and we apply the resolvent to that non-negative function, to be precise, and we want to investigate whether this function is positive or not. And we want to argue here for simplicity by contradiction, namely we want to assume that the corresponding function is not greater or equal everywhere. So let's assume that G is not non-negative throughout, which means that G has some negative values, and by continuity and uniform boundedness, continuity means that there must even be an position x0 where the function G assumes its minimal value, which therefore will be strictly smaller than 0. Now, by applying the maximum principle to the negative, if you like, of that function G, we will see that the operator A, if applied to the function G in this position, then must be non-negative. It's just the inflection of the maximum principle now here for this minimum of the function G. Well, and this can now used to produce a contradiction as follows. We know on the one hand that since G is the resolvent of F, that G is the solution to the corresponding inhomogeneous equation, which involves the operator A and the coefficient lambda, with F as the right-hand side, as the inhomogeneous right-hand side of this equation. We look at this equation, which is correct for any point x. We look at this equation at position x being chosen x0. Since f is assumed to be a non-negative function, this value is greater or equal to 0. On the other hand, at x0, by choice of x0, g at x0 is strictly smaller than 0. So also lambda times g is strictly smaller than 0. Ag is greater or equal to 0. So therefore minus ag is less or equal to 0. So altogether, this here on the right-hand side is a number which is strictly below 0, which is a contradiction because 0 is less or equal to something which is strictly less than 0, which cannot be. This is the contradiction, and therefore G must be non-negative everywhere. Hence we have convinced ourselves that this semigroup TT is in fact a non-negative semigroup. And we have completed our proof of the Hille-Yosida-Ray theorem, which was probably the most abstract theorem of the entire class in this semester. I conclude with two references that you may look up for this particular part. So one is a famous book by Etier and Kurtz. It's called Markov Processes, simply. A classical reference. There's one book which contains basically the proof that I discussed, but I melted it together with some other arguments, which are some paraphrasing. It would basically just paraphrase what's in Etier and Kurtz, which I found in a small book by Ma and Röckner, whose name is Dirichlet Forms. So in either of these two books, basically, you can find the arguments that are presented here in this session in a condensed and hopefully efficient way. So once we have completed this abstract theory, we can from now on work with certain confidence with and analyze Markov processes and use whenever suitable information about the generator when we want to make interesting statements about Markov processes. And we will start now to study specific examples which are interesting in physics, for instance.